In this analysis, we're going to be looking at an industrial fiber laser. This is a very common laser in industry these days for welding, drilling, paint removal, rust removal, and the most common output that we see is running from about 1,000 to 2,000 watts. 1,500 watts we see a lot of in the handheld fiber lasers that are being used for welding and paint and rust removal. So that's what we're going to be looking at, is a 1,500 watt output running 1070 nanometer continuous wave. I will say that these lasers run, up to 50,000 watts. So, we can see all different types of power outputs on these, particularly as we get into heavier welding applications or we need higher speed. We start seeing 3, 4, 5, 6 kilowatt lasers up to 10 kilowatt lasers being fairly common. 50 kilowatts, not so common, but there are some of those out there running. But as I said, for this one, we're going to be looking at 1,500 watts. For the exposure duration for doing our safety calculations, we're going to be using the ANSI default of 10 seconds for a near-infrared wavelength. And we're going to be able to characterize all the outputs of this laser. In other words, the output of the fiber, the collimated beam, and the lens on laser. We'll be able to do all this in one analysis. Now, if we go down and take a look, we can see for a 1070 wavelength that the MPE for continuous wave for 10-second exposure duration, that the MPE is about 5 milliwatts per square centimeter. And I'll go ahead and point out here that even though we're using 10 seconds, you could put 30,000 seconds in here in all-day exposure if you wanted to. And you'll notice that the MPE doesn't change. And you can take a look at the tables in the ANSI standard and see why that is. That according to the tables, from 10 seconds to 30,000 seconds for this wavelength, the MPE, in terms of radiance, is constant. Okay. Now we'll notice that the skin MPE is far less restrictive. It's 1 watt per square centimeter, and right here we're reporting the times skin MPE. In other words, how many times over the MPE is the radiance of the laser, and we can see that it's about 3,400 times the skin MPE. So this has got a serious skin hazard to it. Okay, so let's start by taking a look at, we'll set this back to 10. Let's start by taking a look at the fiber output, because that would be the first thing we would look at. Now, a lot of people, a lot of companies who have this type of laser wouldn't necessarily be getting looking at the fiber output, but then again, you may be doing your own servicing or maintenance on this, and so going ahead and having the analysis for the fiber output is a nice thing to have. It is a multimode fiber with a numerical aperture of 0.22. We arbitrarily set our observer at about 1/4 of a meter. I don't think anybody would be getting any closer than that, really. And we can see that the OD at observer range of 1/4 of a meter for this fiber is rounded off, would be an OD of 4. It has an NOHD of 24 meters. So it's not really all that long, and that's because it has a really high divergence. Okay. Now the next thing we want to look at is the intrabeam. Once the beam has come out of the fiber, we're going to have a lens that's going to collimate this beam before we put it into the focusing lens. Okay, and typically these beams are fairly large because they're reasonable high power. So we kind of see these beams running anywhere from 1 centimeter up to 1.5 centimeters or so. And so this particular laser is running 1 centimeter or 10 millimeters. It had an m² diffraction limit of 1.3, and when we put the 10 millimeter beam diameter in with the m² diffraction limit of 1.3, the software calculates the divergence of 0.177 milliradians or 177 microradians, and of course that's a really low divergence. And for this power level and this wavelength, we can see that the NOHD, this low divergence, is reflected in the NOHD because the NOHD is 49 kilometers. Now, if we want to know what the nominal skin hazard distance is, we can click this cell right here. We can get the NSHD, and we can see that it's about 3.5 kilometers. Okay. Now let's take a look at the lens on laser. We said we had a lens focal length of 250 millimeters. It's right here. This is where we input it. We're using the same beam profile as what we had input into the interbeam. And let me just take a moment here to say it wasn't really specified 1 over e squared, but if you don't know, you can pretty much assume that manufacturers always use 1 over e squared. But again, if we're looking around, we can't find it, we always use 1 over e squared versus 1 over e when we're inputting into the software. The software will convert everything to 1 over e, but if we use 1 over e squared, it gives us a more conservative analysis. So if in doubt, use 1 over e squared. Circular Gaussian, again, if you're not quite sure, you say it may be something between a real Gaussian beam and a flat top beam. Go ahead and select circular Gaussian. Again, that gives us a more conservative result. And so we do the same thing down here. We can see that the collimated beam is 10 millimeters. And so that would be the beam that would be input to the focusing lens. So we put 10 millimeters in for our major and minor axis diameters. We set our observer range at about 1/2 meter. We can see that the OD required is 5.2, and we have a 217 meter NOHD. Let's take a look at a few other things that we can get out of the analysis. Let's take a look at the diffuse reflection here. Now this is set up where we're saying, well, we have a diffuse reflection off of something, maybe an enclosure wall, or maybe we've set up a temporary control area while we're doing some servicing and we're going to terminate the beam and we're looking at it and we want to know the worst case diffuse reflection. So we're saying, well, we're going to scatter 100% of the power off the surface that we're terminating the beam on. We're going to have a direct viewing angle of 0 degrees, and we're going to put a really small beam on target so that we get a point source diffuse reflection. The exposure duration that we typically set for diffuse reflections as a default is 600 seconds, assuming people may be wanting to look at, or service techs or whomever may be wanting to look at the spot using either infrared detectors or some other method for taking a look at the output. So we typically put about 600 seconds in here. But as I mentioned, it doesn't really matter whether you put 10 seconds, 600, or 30 seconds. The MPE is the same. You can see it here. The MPE is the same for 600 seconds as it is for 10 seconds. We can see that we have a point source nominal hazard zone of about 3 meters. That's a pretty large diffuse reflection hazard, and that 1/4 meter away from this, the OD at the observer range is 2.1. We can take a look at the skin diffuse reflection hazard and the MPE and the times MPE here, and we can see that for a diffuse reflection, we don't really have a hazard here, as we're below 1 on the MPE. Now, we may say, yeah, but we don't really have a small beam on target. Wouldn't we have something closer? Maybe we're looking at the collimated beam of 10 millimeters. We can certainly put that in here. And what you're going to notice is that for this observer range, this becomes an extended source. And you can see that what happens is the MPE becomes less restrictive because of the extended source. And if we'd like some information about the extended source factors used, we can come over here to correction factors and time limits, click the interbeam, and we get diffuse, and we can see some of the extended source values that are intermediate values that are used to determine this MPE. Now, I won't get into an extended source. That's for a discussion at another time. But we can certainly put in more realistic beam diameters on target if we want, but if we want the worst case diffuse, just make sure that we put something small in here so that we get a point source type. A couple of other things I want to mention. It's common for a laser like this that we're going to be looking at a barrier to put around this, particularly if we're going to set up a temporary class 4 control area, and we're going to want to know kind of what, how do we, what do we say about the irradiance of this laser for a barrier? And for barriers, what we're after is not the irradiance in the limiting aperture that we see here, but we want the irradiance of the beam. In other words, this beam diameter. And that is reported right here for both the intrabeam lens-on laser and fiber optic. And what we're going to want is the 1 over E. Okay, and so this helps us, this determines what the irradiance is at the observer distance for, say, right here, the intrabeam for the observer distance of 0.5 meter. But if our barrier, say, was going to be set up at 2 meters, we would put 2 meters in here to get this observer. Now, it's not going to change much with this low divergence. We don't see much of a change in the beam diameter at all, so we don't see a real change in the irradiance at that beam diameter. But we do want it in 1 over E, because when we're talking about barriers and we're looking at the barrier standard, the barrier standards are wanting to compare the irradiance in 1 over E. And of course, we have it lens-on laser and fiber optic. Now, the question may be, how do we know what the beam diameter is for a lens-on laser or a fiber optic, okay, like we would know for the intrabeam? And what we can do is come right up here, go to the EZHAZ menu, come down to miscellaneous functions, and look at lens-on laser fiber optic calculations. And we click that, we'll notice we get some information up here, and it gives us the major and minor beam diameters at range, okay, and also it gives us the irradiance at range in the limiting aperture. So we can get the limiting aperture irradiance here along with the beam diameters at the observer distance here. Okay, just wanted to point that out so that information is available. We'll set this back. Okay, and let me see if there's anything else we want to mention here. I think we've pretty much covered everything. So I think that's about it. You can see how we can easily characterize a fiber laser completely from the fiber output all the way to the output to the work piece going through the focusing lens, and we can do it all in one analysis. Then all we have to do is come up and generate a report if we want to generate the report, and we'll have everything we want to know to go along with the information that the LSO needs in terms of a hazard analysis that needs to be on file. Okay, so I think that's about it. Okay.